things for estimating areas under curves. Let's say I just have some generic curve here, y equals f of x. And I want to estimate from A to B the area under the curve. With right-hand endpoints. And in rectangles. So this is just kind of a generic form of what we were just talking about here. So this tells me, I could have said L sub n, M sub n, just the very same, but Rn, right-hand endpoints, n is the number of rectangles, so I'm using that to estimate the area of my curve. Well, since this is kind of generic here, what I wanted to mention here is, well, if I break down my subintervals there, and since I don't know exactly how far this is, I'm just kind of using this as an example, but this first mark, the endpoint of the first subinterval, is usually denoted as x sub 1. And then the next one is x sub 2, so on and so forth until you get to the last one. Now, since I'm going in rectangles, this last one, which is B, is also would also be equivalent to the nth x sub n. So you've got n. In other words, you'll have n x's that you divide this subinterval into. Now, the other interesting note is, what about A? If I called it some type of x, what would I call it? X sub 0, yeah. So the endpoints are x sub 0, x sub n. We usually do refer to them as A to B. Now, the other thing about these subintervals here, I mentioned a while ago that the width of each rectangle, so then the rectangles would be right-hand endpoints, so I'd be going up to here, and then so forth and so on. I'd have n of these little rectangles through here, and then the last one would be right there. So the width of each of those rectangles would be what? Well, it'd be this delta x, we call it. But what is it notationally wise as far as where we're talking about? Well, like we said earlier, what you're going to do is just subtract the endpoints and divide by n, the number of rectangles you want. So delta x, that's an important calculation there. That's b minus a over n. Okay, so that's the width. What about the height of each rectangle? Well, generically speaking, let's think about it. If my function is f of x, what's the height? Well, let's say, what's the height of this first one? Well, it'd be this, but how would I get that out of what I've got? It's f of x sub 1. And then the second rectangle comes in at f of x sub 2. Yeah, it's the function value at whatever x value the width puts you at, right? So in general, we would say the height is f of x sub I, where I is one of these x sub 1, 2, 3, so forth and so on. That's if I'm using right endpoints. So this is the height of the ith rectangle. Okay. Just the generic one, ith one. Okay. It's f of x sub I, because the first one's f of x sub 1. Second one's f of x sub 2. Now, if I change to, that's using right endpoints. If I use left endpoints, Well, the first one would be f of x sub 0. The second one would be f of x sub 1. The third one would be f of x sub 2. So if I use left-hand endpoints, the height of the IS1 is f of x sub I minus 1. Now, one other notation, we'll use this later on too, but just while we're in the mode of notation here. What about midpoints? Well, midpoints are usually denoted with a bar. So this midpoint here would be x sub 1 bar. This midpoint here would be x sub 2 bar. So if I use midpoints, the height would be f of x sub I bar, meaning use the midpoint of your ith interval. So the bar, in this kind of context, the bar means midpoint. Okay? But anyway, more of that to come. Oh, I meant to. No, never mind. Okay. All right. What we're going to do then is now, from our previous examples there from the handout, now we're going to move to to more of a function that we know scenario. So let's talk about this next example here. Okay, so let's use R4 to estimate the area under y equals x squared from x equals 0 to 1. And so, yeah, just again, just a little bit of notation. So what we're talking about, x squared is the parabola. Let me expand it out a little bit. And so that's kind of from 0 to 1 what we're talking about. So I'm talking about this area right here, I'm estimating. And the book's notation, I believe, they'll use is S for that area under the curve. Region S for area under the curve. Okay. All right, so using R4, here's what we get. And just to start us out anyway, let's do it again. So I'm using 4 rectangles from 1 to 4. So what does that tell me the width of each? Well, I'm just going 1 unit, and I want 4 rectangles, so that's going to be a 1/4 width. So each one is 1/4. So you can use fractions or decimals. 0.25. A lot of times we do use decimals here in this context, so it's not bad to use decimals. So we got 0.25, then I got 0.5, and then we got 0.75. All right, but now here's the thing: I can get even better with this because I actually know that this curve here is x squared, right? And so what that means is I can get these heights a lot better. Because what's that height of that first one going to be? Well, it's going to be x squared, isn't it? 0.25 squared. So my area from 0 to 1 is going to be approximately, well, it's going to be 0.25 times, and then the height of it is 0.25 squared. And you can square that out if you wanted to, but and then the second one's going to be 0.25 times what? Well, it's the height here at 0.5. Well, what's the height going to be at 0.5? Well, I know precisely because the height's going to be x squared, so it's 0.5 squared. And then the third one would be the width, 0.25 times 0.75 squared. And these are a little bit longer decimals, so that's why I'm not writing actually out there. And then the last one would be 0.25 times 1 squared, wouldn't it? And so, yeah, I'm just plugging in each time. I can actually plug into the function the x value and get the height precisely. All right. All right, so let's see what that gets us. Again, if you want to, factor off that 0.25, save you a little bit, I guess. And then just do those. You just have to type in 0.25 one time. All right, so 0.25 times 0.25 squared, 0.5 squared, 0.75 squared. I don't know why I wrote 1 squared, because that's going to be 1, isn't it? I get 0.46875 is my approximation. All right, well, just for comparison's sake then, let's, point out here that over or underestimate there for the actual area. Well, again, if you draw in the rectangles here, you can pretty clearly see that that's going to be an overestimate, isn't it? So my actual area is somewhat less than 0.46875, which is not very big anyway, but it's going to be even smaller than that. All right, so what about L4 as our estimate? Well, L4, we're going to have some overlap here, but some not so. The thing about L4 is what? I'm using left-hand endpoints. I'm still using 4 rectangles. However, what about that first one? That first rectangle, well, it really doesn't exist, does it? Because the left-hand endpoint of the first interval is 0, and 0 squared is 0. Okay. And then the second one, now that's where we'd get the 0.25 squared. And then the third one would be 0.25 times, that'd be the 0.5, wouldn't it? So it'd be 0.5 squared. And then the last one is 0.75 squared. Okay, so what does that give me? Well, okay. Basically, it's this add without the 1. All right, so let me redo that. .21875. And so notice there, with this area here, that would be then an underestimate of our actual area. Okay? All right. Well, one thing we could note here is that this does trap the actual area. It gives me a range of values, and so I can safely say that area under the curve is somewhere between these two. It's somewhat more than 0.218 and somewhat more than 0.468. So it's somewhere in that range, definitely. However, how could we improve this? Well, we could improve this. We could use midpoints. But let's talk about adding more rectangles just for a second, because I believe this book probably does it here. Yeah, in the book there is a table, and it's page 285 in this edition of it. But so this is R4, this is L4. Well, come to find out, if we do 8 rectangles, we could do it, but if we did, we would see that R8 is, all right, so in here is 8. R8 is 0.3984. L8, I'll show you why I'm doing it this way. L8 is 0.273. So if I've got in rectangles, 8 rectangles, R sub 8 is 0.3984, L sub n is 0.273. So that represents, what was this, 4, 6? That represents a little better, little smaller range, right? Now, what the table in the book does is they go into more and more rectangles. If it has 10, well, here it is, 0.285, and then RN, I've got them backwards from what it was in the book, 0.385. If it's 20, it's 0.308, 0.3587. Let's jump to 50. It's 0.323, 0.343. Do it backwards again. I should have done this the other way. Okay. All right. 100. Well, it's 0.338 for R, and then 0.328 for L, and then for 1,000, 0.332, 0.33. Well, both of them basically 333. This might be 334. All right. Okay. The reason I mention that is because this kind of correlates with something we did previously. Remember doing something like this with slopes? We did something vaguely similar to this with slopes, where we took those slopes of the secant lines, and that ultimately led us to the slope of the tangent line, and ultimately led us to derivatives. Well, this is sort of growing it won't go to derivatives, but we'll talk about that later. But you kind of see that it looks like the area is getting trapped here between 0.334 and 0.333. It looks like it's going to 1/3, doesn't it? Hopefully get the idea. So yeah, both of these seems like we're headed to 0.33333. Yeah, that'd be 1/3, wouldn't it? And it turns out that is actually the area. We'll say more about that later. But then, you know, why do these do a better job? Well, it's because you have more rectangles, and so if you look on page 287 there, they've got 30, 50, 30 rectangles up to 50 rectangles. 50 is doing a pretty good job, isn't it? Because there's not a whole lot of gap that you see between the I mean, your little rectangles are not very wide at all, so yeah, you're getting very, very small rectangles, and so yeah, there's not as much gap, not as much wasted space, so to speak. Okay? All right. So let's do another one of those, finish out today with. That gives you a good idea of kind of where we're going with this. More and more rectangles is better, right? 3 is good. 10 is better. 1,000 better. There's even better than that. Okay? All right. So let's estimate for this one. Estimate the area under the curve y equals x to the f of x equals x to the 4th plus x squared from x equals 1 to 3 Number one, using R5 again? Yeah, R5. One to 3, x to the fourth, let's see what that looks like. X to the fourth plus x squared, what does that look like? Okay, well, it's kind of like a parabola looking thing. But I'm only looking from 1 to 3. Oh, yeah. Which brings up another. That 3, well, it's off of mine. That 3 is going to be way, way on up there because you're talking, what, 81 plus 9. That's up to 90. So that's the first issue there, and 1 is way down here at 2. So, yeah, this goes from 2 to 90 there. But there's some other issues here. So I'm going to estimate that thing right there, area under that curve, using R5. Okay, well, first of all, let's figure out this delta x, the width of my rectangle. We call it, what is it? Each rectangle. Well, we've got 2 units, 3 minus 1, divide that by 5, hey, that's 0.4. So the width of them is going to be 0.4. Okay? All right, well, here's another thing then. If I'm using R5, then, you know, each one of these rectangles, each one of these rectangles is going to be 0.4 wide. So the first one's at 0.4. What about the height of the first one? Well, the height is going to be whatever the function value. If I'm using function notation, couldn't I write it this way? And then the second one would be 0.4 times, well, it'd be, go over 0.4 more, that'd be 0.8. And then the third one would be, add 0.4 more, would be the function value at 1.2. How many got? 5? Okay, so I got 2 more. So the third one would be 0.4 times f of, what's the next one? 1.6? Whoops. Wrong. Okay, let's start this over. The first one is, I'm starting at 1, aren't I? So it's 1.4, and then 1.8, and then 2.2. Sorry about that. The third one would be 2.2, the fourth one would be 2.6, and then the last one would be 0.4 times, that would be the f of 3. I knew I was in trouble because the endpoint is supposed to be 3, and I wasn't going to get there. So, all right. Now, one reason for me writing, I mean, you can do the 1.4 to the fourth plus 1.4 squared. You can put that in accordingly. I mean, you can just say this is 1.4 to the fourth plus 1.4 squared. You can put it in like that if you want to. Okay, that's fine. But let me show you this other way, since we have our handy-dandy graphing calculators, on the TIs anyway. There's a way you can get, you can plug in, if you've got your, I plug my curve into y1, so I'm going to use y1. What I'm going to do is, for f of 1.4, I'm going to put in this notation, y1 of 1.4. And here's how you do that on the TIs anyway. On the TIs, there's a button right under the arrows called vars. So if you go to vars and then go to yvars, variables is what that means, then scroll arrow over to yvars, and then we're putting them in as functions. So number 1, you should get a listing there of all the y1, y2, y3. So depending on where you put this one in, that's one we're going to pick. I did just so I had put it in y1 there. So what I can do is I can put this in, like I said, you can just put the 0.4 in once, and then I'm going to put in y1 of 1.4. So what you have to do is from the computation screen, go through that process if you weren't there already. All right, so let me start over. All right, so I'm going to put in my 0.4, and then I'm going to put parentheses, and then I'm going to go to that vars, y-vars screen. And then it's just like the function notation. Just put parentheses around your first endpoint there, 1.4. Whoops. And then we're going to do plus y1 of 1.8, and then plus y1 of 2.2. With me? And it'll do all the work for me there. Won't have to put in all those things, which is very helpful if you've got, you know, a bigger function. We got 2.2. What's the next one? 2.6. So y1 of 2.6, and then the last one is, that'd be 90, but so it's just a nice way of getting these estimates. Did anybody else get 76.104? Huh? That's what you got? Okay. All right. Let's do one more. Number 2, same thing, but let's use M5. And so when you're doing these, you know, the big deal is getting those endpoints of your interval set up nicely. Let me try to get these correctly this time. So I'm going 1 to 3. It's a little taller than that, but we'll call that one good. All right, so if I use midpoints, yeah, I'm dividing this up into 0.4s. Okay, so the first one would be 1.4 endpoint, then 1.8, and then 2.2, and then 2.6, and 2.6 plus 0.4 is 3. All right, but I want to use midpoints, so those are helpful, but I'm interested in midpoints. Well, what's the midpoint of this one going to be? Well, it's halfway between 1 and 1.2, 1.4s, which is 1.2. And then halfway between there, and then again note these midpoints, you know, once you get the first one, then the next one's 0.4 over, then the next one's, the midpoint there would be 0.4 over, and then the next one's 0.4 over, 2.8. I don't know if you can see all that, but anyway, here's what I get. First midpoint. All right, so what you might do when you're doing these midpoints, one suggestion, if you get them accurate here, you might not be able to see all that. Yeah, my x1, of course I started at 1. My x1 was 1.4. My x2 was 1.8. x3. May not have to go in all this, but last one's 3. All right, so x sub 1 bar is 1.2. It's halfway between these two. X sub 2 bar is halfway between those two. It'd be 1.6. Then x sub 3 bar is 2. X sub 4 bar is 2.4. And then x sub 5 bar, the fifth one, is 2.8. And so those are the ones that I use here for my function values. Plug those in to get my function values. All right, so M5 then would be, I would take 0.4 times all those. So that would be y1 of 1.2, y1 of 1.6, y1 of 2, y1 of 2.4, and y1 of 2.8. Going off the screen here. All right. So we can figure those out. Since I got those already in there, let me see. Change them up. 1.2, 1.6, 2, 2.4, and then 2.8. I just called back my entry from my previous. Yeah. Then you just change 56.34. And again, that's 348. That's a pretty good estimate because you see there that would be that. If you draw in the rectangles there. That's pretty good because like I said, you got some give and you got some take.